So in the past, we've looked at one variable inequalities. Now we're going to be looking at two variable inequalities. So if you can recall doing problems like this, x less than 3, whenever we graph that, we plot the coordinate 3, and then we have an open dot on 3. And less than, since my variable is on the left, I would shade to the left. So the possible solutions for this inequality are in the shaded region. If I'm greater than, then I plot my 3. Still an open dot because it's just greater than, there's no equal to, and I shade to the right. So all of these solutions are over here in the shaded region. Less than or equal to, now I have a closed dot and I shade to the left. Greater than, equal to, again, closed dot and shade to the right. So the solutions to the inequality for the greater than, equal to, less than, equal to include the value 3 and then include the shaded region because of the equal to sign and the closed dot. So let's take that idea of shading when we have inequalities and now take it to two variables. So instead of just having an x number line, an x-axis, now we have an x and a y, so I can graph lines as well as the absolute value functions. So whenever I have greater than or less than, I do not have an equal to sign. That means that I am going to have a dashed line in my function. Okay? If I have a less than or equal to or greater than or equal to, I'm going to have a solid line because my inequality solutions will include that line. Every single coordinate on that line is part of the solution set. If it's dashed, that means that those are not part of the solutions. Now, how do I know where to shade? Now, y describes the vertical position, right? So my y-axis is a vertical line. So the y describes the vertical position. So the solutions here, if I have y greater than a line or y greater than our absolute value function, we want to shade above the boundary line, so towards the positive direction of y. If it's less than or equal to, I'm going to shade below the boundary line towards the negative values of y. If you're still not sure whether or not you shaded in the right region, then you can pick a test point. So pick a value in the region that you think should be in the shaded region. Do not pick a point that's actually on the boundary line, okay? So pick a point that should be in this shaded region and then plug it into the equation and see if it makes a true statement. If it makes a true statement, then we have picked and shaded the correct side. If it doesn't, then we need to shade the opposite side of the boundary line. So let's graph this. Y is less than negative 2x plus 1. So the first step is to graph the boundary line. So the boundary line is what it looks like without the inequality. So y equals negative 2x plus 1. So that's a y-intercept of 1, slope of negative 2, so down 2 to the right 1, down 2 to the right 1. I can also go up 2 to the left 1. Now, because my inequality here is less than, there's no equal to sign, I know I'm going to have a dashed line, which means that all of those points that are on this line are not part of the solution. Now, I have y is less than negative 2x plus 1, less than. So, you look at your y-axis. Less than, I want to get small. So where are the y values going to decrease? Where are they getting smaller? They're getting smaller down here because those are the negative values. So that is where I am going to shade. So you do your best effort to shade. I understand that you're not going to get a solid shading, but shade as much as you can. This is also why we extend the line, because we need to shade everything to the left of that line that is part of the solution. So that means that every single point in the shaded region works when I plug it in. Every single point will make it true. Let's just test that out. So let's say I want to do negative 2, negative 4. So here's negative 2, negative 4. Let's plug that in. So y is negative 4. X is negative 2, Let's see if this is a true statement. Is -4 less than +5? Yes, it is. So this is a true statement, so we know that we shaded the correct region of the graph. Now, even though all of the points on the boundary line are not part of the solution, because we're graphing, we still need to label at least 3 points and label your x and y axis as well. So when you're given the graph of an inequality and asked to write the equation, this is much like given the graph of just the line and asked to write the equation. We have a few other things we have to take into account, but first let's just find the equation of the boundary line. So for this type of line, it's going to have a slope. The slope is 3/2. I rise 3 and run 2 to get to the next point. I'm actually given the y-intercept. The y-intercept is 2. So I can jump right to y equals mx plus b form, slope-intercept form. So this is the equation of the boundary line. So now I need to take into consideration where am I shaded and am I solid or dashed. So this is a solid line, so I'm going to have an equal to, and I'm shading towards the negative values of y, so it's going to be less than. So I'm going to have y is less than or equal to because it's solid, and then my boundary line. Now on the right-hand side, this line's a little bit different. It's a vertical line, so I know vertical lines have the equation x equals, and it's going to be x equals -3. So because I have a dash line, I know that I'm not going to have an equal to symbol. And this is a little different because I don't have y values that I'm looking at. For this line in particular, I want to shade values that are bigger than -3, right? So all of these x values are bigger than -3. So I want to shade x greater than -3. I do not have an equal to symbol because it's dashed, and this says all the x values bigger than -3, and that is all the x values bigger than -3. So let's graph this absolute value inequality. So I have two types of transformations going on. This minus here tells me that I'm going to reflect over the x-axis. The +1 on the outside tells me that I'm going to shift up 1. So my parent function points are all going to reflect over the x-axis and then shift up 1. So here are my new points. So this is what we kind of think of as my boundary line. Now it's not a line, it's my boundary function. So now I need to determine, is it going to be solid or dashed? Well, because of this equal to symbol, I know it's going to be solid. So far, all we've graphed is y equal to negative absolute value of x plus 1. So now we have to take into account the shading. So I want to shade for y values that are bigger than this function. All the y values greater than this function. So that is going to be towards the positive y values, which is above. So I'm going to shade above. Now this is why you need to extend your lines when you're graphing to make sure that I am shading all the correct regions of the coordinate plane. And shade as much as you can. With a pencil, it might be a little bit easier to just shade. So let's label our vertex here. My vertex is 0, 1. My h is 0, my k was 1. Let's label some more points here. Label your x and y axis. And if you would like, you can pick a test point to make sure that you shaded the correct region. So pick any point that's in the shaded part and make sure it works when you plug it in to see if you shaded the right region. Remember, we never pick points on the boundary line. So much like writing the equation of an inequality for a line, for the absolute value function, you just find the boundary function. So what is the equation of this v function? And then we're going to look at the inequalities. So from the vertex 0, 0, we went right 3, down 2, which means right 3, h is a positive 3, k is going to be a negative 2 because we went down 2. So my boundary function is going to be y equals the absolute value of x minus 3 minus 2. Now, because I am a dashed line, that means I'm not going to have an equal to symbol, and I'm shading towards the positive values of y, so it's going to be greater than. So y greater than the absolute value of x minus 3 minus 2. No equal to because it's dash, and it's greater because I'm shading towards the positive y values. And again, you could pick a test point if you would like to verify. Give these problems a try.